Hello, everyone. In this section, we will introduce the basic properties of semiconductor materials in electronics. Since today's very large-scale integrated circuit devices are made using semiconductor materials and semiconductor processes, understanding the basic properties of semiconductors is also very important. The source material mainly used in today's very large-scale integrated circuit manufacturing is silicon. Silicon is a group 4 element. Its atomic number is 14. This means the nucleus has 14 protons with a charge of positive 14Q. Its electron configuration is: the first shell has 2 electrons in the 1s subshell. The second shell has 2 electrons in the 2s subshell and 6 electrons in the 2p subshell. The third shell has 2 electrons in the 3s subshell and 2 electrons in the 3p subshell. This means the total number of electrons is 14, and the outermost shell, which has principal quantum number n equals 3, contains 4 electrons. This represents a neutral silicon atom. The nucleus, with positive 14Q, together with the 10 inner shell electrons in the n equals 1 and n equals 2 shells, forms an inner core with a total charge of positive 4Q. This core becomes neutral together with the 4 electrons in the outer shell, where n equals 3. Therefore, a silicon atom can be simplified as shown in the diagram on the slide. Silicon atoms can bond with other silicon atoms through covalent bonds. Two neighboring silicon atoms each contribute 1 electron to form a covalent bond. The electrons that form covalent bonds are also called valence electrons. When many silicon atoms are periodically arranged and bonded together, they form the source material for electronic devices, a silicon crystal. A semiconductor without any other impurity elements is called an intrinsic semiconductor. For intrinsic silicon at room temperature, where T equals 300 Kelvin, a small number of valence electrons absorb thermal energy from the environment. They break free from the covalent bond constraint and transition from a lower electronic energy level to a higher electronic energy level, forming nearly free electrons, as shown in the figure. From the energy space point of view, the valence electrons that form covalent bonds have energy levels inside the valence band. After absorbing thermal energy, they transition to higher energy levels inside the conduction band. Electrons in the conduction band that have escaped from covalent bond constraint can be regarded as free electrons. They can move under the force of an electric field and form current. The empty electron position in a covalent bond is called a hole, as shown in the figure. Therefore, for an intrinsic semiconductor, whenever one valence electron moves from the valence band to the conduction band, one hole must be generated in the valence band. As a result, the number of electrons in the conduction band equals the number of holes in the valence band. When no holes are generated, the intrinsic semiconductor is electrically neutral, as shown in the local region at the lower right of the figure. At the place where a hole is generated, one electron charge, negative Q, is missing. Therefore, the original neutral position becomes locally positively charged by positive Q after the electron transitions away. We can understand this as follows. The silicon atom has an inner core, formed by the nucleus and inner shell electrons, with charge positive 4Q. Originally, the outer shell has 4 electrons with a total charge of negative 4Q, so the total charge is positive 4Q plus negative 4Q, which equals 0, making it neutral. When one electron leaves, the total charge of this atom becomes the inner core charge, positive 4Q, plus the remaining 3 outer shell electrons, negative 3Q. The result is a positive charge of positive Q. Therefore, a hole can be regarded as an equivalent positive charge. When a hole exists in the valence band, it means there's an empty position for a valence electron. A valence electron near the hole can also move into the hole position because of thermal energy, forming a covalent bond. The final result looks as if the hole, which is an equivalent charge of positive Q, has moved to the position where the valence electron came from. The change in total charge is therefore equivalent to the movement of a hole carrying positive Q. As a result, hole movement in the valence band can also form current. Therefore, in a semiconductor, the charge carriers that can form current are electrons in the conduction band and holes in the valence band. The concentration of electrons in the conduction band is represented by the symbol N, because electrons carry negative charge, so N comes from negative. Similarly, the concentration of holes in the valence band is represented by the symbol P, because holes carry an equivalent positive charge, so P comes from positive. Concentration means the number per unit volume. Usually, cubic centimeter is used as the volume unit, so the unit of concentration is the number of conduction band electrons or valence band holes per cubic centimeter. For intrinsic silicon, the atomic density is about 5 times 10 to the 22nd silicon atoms per cubic centimeter. At room temperature, T equals 300 Kelvin. Only a very small number of valence electrons can absorb thermal energy from the environment and transition to the conduction band to become conduction electrons. The concentration is about 1.5 times 10 to the 10th conduction electrons per cubic centimeter. For an intrinsic semiconductor, every time one valence electron transitions out, one hole must be generated. Therefore, the conduction band electron concentration equals the valence band hole concentration. Under thermal equilibrium, the symbols N and P have a subscript I, meaning intrinsic. Therefore, Ni equals Pi equals 1.5 times 10 to the 10th. The intrinsic carrier concentration is formed because valence electrons in the valence band absorb thermal energy from the environment and transition to the higher energy conduction band, generating conduction electrons and holes. Therefore, the intrinsic carrier concentration is strongly related to the environmental temperature. It is also related to the energy difference between the conduction band and the valence band. This energy difference is called the band gap, represented by Eg. For silicon, Eg equals 1.12 electron volts. Therefore, Ni squared equals a material constant B multiplied by T cubed, and then multiplied by the exponential of negative Eg divided by kT. The higher the temperature, the higher the environmental thermal energy. As the thermal energy of valence electrons increases, the probability that they can transition to the conduction band increases, which increases the intrinsic carrier concentration. From the equation, we can see that Ni is a strong function of temperature. This point is very important. It means that the electrical characteristics of electronic devices made from semiconductor materials are strongly related to temperature. In addition, under thermal equilibrium, carrier concentration symbols in semiconductors use a subscript 0, such as N0 and P0. Under thermal equilibrium, the product of the conduction band electron concentration and the valence band hole concentration equals Ni squared. This property also applies to semiconductors with impurities added, not only to intrinsic semiconductors. Because the carrier concentration of an intrinsic semiconductor is very low, its conductivity is poor. It lies between a conductor and an insulator, so it is called a semiconductor. In order to increase conductivity, we must adjust the carrier concentration inside the semiconductor. Therefore, other elements must be added into the intrinsic semiconductor. Since the added element is different from the semiconductor material itself, it is called an impurity. In Chinese, the word impurity may sound like something bad, but that is not the meaning here in semiconductors. It simply means an element different from the semiconductor material itself. The action of adding impurities into a semiconductor is called doping, so the added impurity can also be called a dopant. A semiconductor with dopants added is called an extrinsic semiconductor. As mentioned earlier, silicon is a group 4 element. Its atomic diagram can be simplified as an inner core with a charge of positive 4Q. This core consists of the 14 protons in the nucleus plus the 10 inner shell electrons, together with 4 electrons in the outermost shell. For group 4 semiconductor material silicon, dopants can be divided into 2 main categories. The first category is group 5 elements, mainly phosphorus and arsenic. Taking arsenic as an example, the inner core of a group 5 element has a charge of positive 5Q, formed by the protons in the nucleus and the inner shell electrons. The outermost shell has 5 electrons, forming a neutral arsenic atom. If one neutral group 5 element replaces one neutral silicon atom in the silicon crystal, the semiconductor is still neutral. However, as shown in the figure on the right, arsenic has 5 outer shell electrons. 4 of them form covalent bonds with neighboring silicon atoms and become valence electrons in the valence band. The 5th electron becomes a weakly bound electron. At ordinary environmental temperature, this fifth electron has enough thermal energy to escape the binding of the arsenic nucleus and become a free electron in the conduction band. Notice that each group 5 element doped into the silicon crystal generates one free electron. At the same time, this free electron is generated without producing a hole. This is different from an intrinsic semiconductor. In an intrinsic semiconductor, the number of electrons in the conduction band equals the number of holes in the valence band. In an extrinsic semiconductor, the electron concentration and hole concentration are not equal. However, when the fifth electron of the group 5 element, which does not form a covalent bond, escapes the binding of the nucleus and becomes a free electron in the conduction band, it moves away. Then the group 5 atom position carries a local positive charge. This local charge occurs because the inner core of the group 5 atom has charge positive 5q, while only 4 electrons remain in the outer shell. Therefore, a local positively charged region is formed inside the semiconductor. This charge is called space charge, and it is immobile. To summarize, inside a group 4 silicon crystal, once group 5 elements are doped in, each group 5 atom contributes 1 electron. Therefore, group 5 dopants are called donors, meaning they give electrons. The concentration of doped donors is represented by Nd. N represents concentration, and the subscript D means donor. Its unit is the number per cubic centimeter. In general, the Nd concentration is about 10 to the 15th to 10 to the 20th, which is much larger than the intrinsic carrier concentration. Under thermal equilibrium, the doping concentration is approximately equal to the electron concentration in the conduction band. Therefore, Nd is approximately equal to N0. As mentioned earlier, under thermal equilibrium, the product of the electron concentration and the hole concentration inside a semiconductor equals Ni squared. This property also applies to extrinsic semiconductors. Therefore, for a semiconductor doped with donor concentration Nd, its hole concentration is approximately Ni squared divided by Nd. Under general conditions, the electron concentration N0 is much larger than the hole concentration P0. Therefore, in a donor-doped semiconductor, among the two mobile carriers, electrons in the conduction band and holes in the valence band, electrons are the majority carriers and holes are the minority carriers. A semiconductor whose majority carriers are electrons is called an N-type semiconductor. The name N comes from the symbol for the electron concentration. To label the electron concentration and hole concentration in an N-type semiconductor more clearly, the symbols usually include an additional subscript N representing carriers in an N-type semiconductor. Therefore, under thermal equilibrium, the electron concentration in an N-type semiconductor is written as NN0, and the hole concentration is written as PN0. If it is not under thermal equilibrium, the subscript 0 is not used. The concentration symbol for the space charge is Nd+. Under ordinary conditions, the dopant Nd fully ionizes and releases electrons. After the released electrons leave, Nd ions remain. Therefore, the donor space charge is written as Nd+. In addition to group 5 dopants, group 3 elements are also commonly doped into silicon semiconductor crystals. Taking boron as an example, the inner core of a group 3 element has a charge of positive 3q, formed by the protons in the nucleus and the inner shell electrons. The outermost shell has 3 electrons, forming a neutral boron atom. If one neutral group 3 element replaces one neutral silicon atom in the silicon crystal, the semiconductor is still neutral. However, as shown in the figure on the right, boron has 3 outer shell electrons. All 3 electrons form covalent bonds with neighboring silicon atoms and become valence electrons in the valence band. However, the covalent bond with the 4th neighboring silicon atom is missing one valence electron. In other words, there is an empty position for a valence electron, and this is a hole. At ordinary environmental temperature, this empty electron position, which is the hole, can be filled by a nearby valence electron moving because of thermal energy. This is equivalent to the movement of an effective hole carrier. Notice that each group 3 element doped into the silicon crystal generates one hole in the valence band. At the same time, this hole is generated without creating an additional electron in the conduction band. This is different from an intrinsic semiconductor. However, When the covalent bond vacancy, or hole, of the group 3 element moves away because of another force, the group 3 atom position carries a local negative charge. This local charge occurs because the inner core of the group 3 atom has charge positive 3q, while the outer shell has 4 valence electrons after being filled by an electron. Therefore, a local negatively charged region is formed inside the semiconductor. This charge is called space charge, and it is immobile. To summarize, inside a group 4 silicon crystal, once group 3 elements are doped in, each group 3 atom contributes one hole. Because a hole is an empty position for an electron and can accept an electron, group 3 dopants are called acceptors. The concentration of doped acceptors is represented by Na. N represents concentration, and the subscript A means acceptor. Its unit is the number per cubic centimeter. In general, the Na concentration is about 10 to the 15th to 10 to the 20th, which is much larger than the intrinsic carrier concentration. Under thermal equilibrium, the doping concentration is approximately equal to the whole concentration in the valence band. Therefore, Na is approximately equal to P0. As mentioned earlier, under thermal equilibrium, the product of the electron concentration and the hole concentration inside a semiconductor equals Ni squared. This property also applies to extrinsic semiconductors. Therefore, for a semiconductor doped with acceptor concentration Na, its electron concentration is approximately Ni squared divided by Na. Under general conditions, the hole concentration P0 is much larger than the electron concentration N0. Therefore, in an acceptor-doped semiconductor, among the two mobile carriers, electrons in the conduction band and holes in the valence band, holes are the majority carriers, and electrons are the minority carriers. A semiconductor whose majority carriers are holes is called a p-type semiconductor. The name P comes from the symbol for the hole concentration. To label the electron concentration and hole concentration in a p-type semiconductor more clearly, the symbols usually include an additional subscript P, representing carriers in a p-type semiconductor. Therefore, under thermal equilibrium, the hole concentration in a p-type semiconductor is written as Pp0, and the electron concentration is written as Np0. If it is not under thermal equilibrium, the subscript 0 is not used. The concentration symbol for the space charge is Na-. Under ordinary conditions, the dopant Na fully ionizes and releases holes. After the released holes leave, Na ions remain. Therefore, the acceptor space charge is written as Na-. Finally, let us summarize the comparison between p-type and n-type semiconductors. Under thermal equilibrium, a semiconductor whose electron concentration is higher than its hole concentration is called an n-type semiconductor. Conversely, a semiconductor whose hole concentration is higher than its electron concentration is called a p-type semiconductor. Their symbols are also different. Doping with group 5 elements can increase the electron concentration in the conduction band, and this type of dopant is called a donor. Doping with group 3 elements can increase the hole concentration in the valence band, and this type of dopant is called an acceptor. That concludes the basic introduction to semiconductor materials. Please look forward to the next class. See you next time. Bye-bye.